Jai Hind everyone. I am Krishna Gupta. I am assistant professor in Electronics and Communication Engineering Department in Ajay Kumar Garg Engineering College. This is lecture 1 of the subject integrated circuits, and in this lecture I am going to discuss the basics of operational amplifier. In short, that operational amplifier is called op-amp. So in this class I will firstly start with the operational amplifier. We will define the op-amp, what is op-amp, what is the role of the op-amp, what are the applications, advantages of op-amp, and after that ideal op-amp characteristics. Then we will discuss about the block diagram and equivalent circuit of operational amplifier. So starting with the operational amplifier, basically as the name suggests, operational means it is used to perform different operations. Operational amplifier is the amplifier which is used to perform different operations, and the beauty of this operational amplifier is that it amplifies the difference between two signals, difference between two input signals. So this difference word is very much important, because already we had studied this amplifier like common emitter amplifier, common source amplifier, right? And in common emitter, common source amplifier, we apply a single input at the base and gate of the BJT and MOSFET. But in operational amplifier, it amplifies the difference. That is the difference between the normal common emitter, common source amplifier and operational amplifier. And the advantage of this operational amplifier, one of the advantage is the effect of noise is very less in case of operational amplifier. That's why operational amplifier, it is very much used in the design of various circuits like oscillators. Apart from oscillators, active filters are there, right? So there are various other advantages also, and we'll discuss about it in further slides. And another important feature of this operational amplifier is it is a multi-stage amplifier. It is a multi-stage amplifier. Normally op-amp is a multi-stage amplifier. Multi-stage amplifier means it is having more than one stage. So when we go for multi-stage amplifier, the advantage is we get high gain. So like 2 stage, 3 stage, 4 stage amplifiers, all are multi-stage amplifier. And initially when this operational amplifier was invented, it was used to perform different operations. For example, addition, subtraction, multiplication, division, integration, differentiation, then log amplifier as a log amplifier, as an anti-log amplifier. So there are various other applications also. So these operations can be performed with the help of operational amplifier. That's why it is called operational. And another thing about operational amplifier is it is a high gain amplifier. It is a high gain because it is a multi-stage amplifier. It is a multi-stage amplifier. And as far as operational amplifier is concerned, it is having two input terminals. This is the basic schematic symbol of operational amplifier. It is having two input terminals. One is inverting input, that is the negative one, and another one is the non-inverting input, that is the positive one, right? This is the basic symbol of operational amplifier, that is called op-amp. And there are various op-amp ICs available in the market, and one of the most popular IC that is available, that is 741 IC. 741 IC. So in 741 IC, it requires two power supplies. One is plus VCC and another one is minus VCC. So some op-amps require single supply, but 741 it requires two power supplies. So in short, we can say that operational amplifier is very much useful because it provides high gain and effect of noise is very less in case of operational amplifier. Now coming to the ideal op-amp. What should be the characteristics of ideal op-amp? Once we understand the characteristics of the ideal op-amp, then we can understand that what should be the value of the input impedance, output impedance, bandwidth, gain for any practical amplifier also. So this is the reference, this is for the reference. So for ideal op-amp, we say that the open loop gain that is in short called AOL, it should be infinite. Now firstly we need to understand that what is this open loop gain? What is this open loop gain? So to understand it, let's again draw this schematic symbol of operational amplifier. Let's say V1 voltage is applied at the non-inverting terminal, V2 voltage is applied at the inverting terminal, and the output voltage of this operational amplifier is V0. Fine. So you can see that there is no feedback path. So this op-amp is in open loop configuration. So we can calculate the gain of this operational amplifier. That gain will be called AOL because there is no feedback path, open loop gain. It will be output voltage upon input differential voltage, because operational amplifier is basically a difference amplifier. It amplifies the difference between two signals, and these two signals are V1 and V2. So AOL will be V0 upon the voltage at the non-inverting terminal voltage minus the voltage at the inverting terminal voltage. So AOL is V0 upon V1 minus V2. For ideal op-amp, it should be infinite. So if AOL is infinite, it means that V1 minus V2 should be 0. If V1 minus V2 is 0, then V1 equal to V2, and this concept is very much useful to understand the virtual ground concept, especially in the inverting amplifiers. Fine. Now coming to the next characteristics of ideal op-amp, that is bandwidth of the ideal op-amp should be infinite. So the bandwidth is the range of frequency over which we can use that op-amp. Fine. If the bandwidth is infinite, it means that it can amplify very low frequency as well as it can amplify very high frequency, right? And this operational amplifier, it can amplify the DC as well as AC. Now the third characteristics of ideal op-amp, that is the input impedance. Since this operational amplifier is a voltage amplifier, so the input impedance should be infinite, and for any voltage amplifier it is desirable that the output impedance should be 0. So this is required, and this is very much desirable for voltage amplifier. The input impedance should be high and output impedance should be 0 in order to avoid the signal loss. Now the next parameter is CMRR. CMRR, it stands for common mode rejection ratio. It should be infinite for any op-amp. This is the ideal case. CMRR should be infinite. Now we need to understand that what is this CMRR. So we can define this CMRR. CMRR is defined as differential mode gain AD upon common mode gain ACM. Differential mode gain AD upon common mode gain ACM. So here the differential mode gain, it will be the normal gain like V0 upon V1 minus V2. But to calculate the common mode gain, we need to apply the same input signal at both the input terminals, that is the inverting terminal and the non-inverting terminal, at both the input terminals, right? And this common mode signal is basically the noise signal, and of course we want that the effect of noise, it should be 0, it should be minimum for any analog circuits, right? So whatever noise is being added here at the input, it should not propagate from input to output. We need to reject this noise. We need to cancel out this noise. So to cancel out this noise, this op-amp is very much useful, because if the voltage at the both the input terminals is same, since it's a difference amplifier, so the difference will be 0. So no noise will propagate from input to output. That's the important aspect of the operational amplifier. So coming to the next parameter, that is slew rate. In short, it is called SR. SR, that is slew rate. For any op-amp, ideal op-amp, slew rate should be infinite. So slew rate is defined as, we can say that Slew rate is maximum rate of change of output voltage. Maximum rate of change of output voltage with respect to time. With respect to time. So we can find out we can understand the speed of the circuit with the help of slew rate. And of course, if the slew rate is good, if the slew rate is high, then the response of the circuit will be faster. So in short, we can say that these are few parameters for op-amp. There are other parameters also like PSRR, power supply rejection ratio, offset voltage, bias current, offset current, but these are few important parameters which is required at every stage to understand op-amp. Now coming to the block diagram of operational amplifier. See, like I had mentioned that this operational amplifier is a multi-stage amplifier. Normally it is a multi-stage amplifier, and the first stage of any op-amp, it will be always a differential amplifier. The first stage will be a differential amplifier. It is very much required because differential amplifier is the amplifier which amplifies the difference between two signals, right? So we can say that this is the first stage, or we can say that this is the input stage. This is the input stage, and the input signal, it is applied at the differential amplifier. Let's say this input differential voltage is VID. Input differential voltage is VID. So this is the first stage, that is the input stage. Now we had studied this differential amplifier in analog circuits also. So there are various configurations of differential amplifier like dual input, balanced output, dual input, single-ended output. So there are four configurations for differential amplifier. So normally the first stage is the dual input, balanced output. Balanced output means we take the output from two terminals, right? So this is the dual input, balanced output. And after the first stage, the next stage, that is called intermediate stage. Intermediate stage. So basically this intermediate stage is normally dual input, unbalanced output. Means it gives the single-ended output, because in many applications it is required single-ended output, right? Like you can see that the first stage, it is giving balanced output, right? There are two wires coming out, but after the intermediate stage, there is a single wire. It's a single-ended output, right? Although this is not the mandatory requirement for every op-amp, in some op-amp there are two differential amplifier. Like the first stage is dual input, balanced output differential amplifier. The second stage is again a balanced dual input and single-ended output, right? So this intermediate stage, it can be again a differential amplifier. And after that, the third stage, next stage is the level shifter. Level shifter circuit. Level shifter. The role of the level shifter is to shift the DC level of the signal, to shift the DC level of the signal. And after the level shifter, the last stage, that is called output stage. Output stage. And from the output stage, we take the output. Let's say this output voltage is V0, right? Normally this output stage of op-amp is push-pull configuration. Push-pull configuration, like if we take the example of 741 IC, in 741 IC the output stage is class AB push-pull output stage, right? So these four are the major blocks of the op-amp. But see, this is the general block diagram, right? Like in this block diagram, you can see that the first two stages are the differential amplifier. But in some op-amps, only the first stage is the differential amplifier. But it is important that the input stage, that is the first stage of every op-amp, should be differential amplifier. Why? Because there is a noise in the circuit, and that noise should not propagate from input to output. That noise should not get amplified. Fine. So for that, we need to cancel out that noise to cancel out that noise, it is very important that the input stays, it should be differential amplifier. So this is the general block diagram of operational amplifier. Now coming to the schematic symbol of op-amp. So schematic symbol that I had already mentioned, in operational amplifier there are two input terminals. Let's say V1 voltage is applied at the non-inverting terminal, V2 voltage is applied at the inverting terminal, and output voltage is V0. So we can say this is the schematic symbol of op-amp. This op-amp is basically the voltage amplifier having two input terminals. If we talk about one of the op-amp IC like 741 IC, so in 741 IC, since there are two supplies required, so we can add two supplies, one is plus VCC and another one is minus VCC, plus minus VCC. That is the schematic symbol of, we can say, 741 IC, right? Now coming to the equivalent circuit of op-amp. So to understand the equivalent circuit, firstly we need to understand that this op-amp is basically the voltage amplifier. So the input is voltage and the output is voltage. So we can easily draw this equivalent circuit. So to draw the equivalent circuit, we need to mention the input resistance, output resistance, input voltage and output voltage. Let's say the input resistance, resistance of the op-amp is Ri. This is Ri, right? And you know that this op-amp is having two input terminals, right? One is positive, another one is negative. Positive is the non-inverting terminal and negative is the inverting terminal. So let's say this is positive terminal, this one is negative terminal, and V1 voltage is applied at the non-inverting terminal, V2 voltage is applied at the inverting terminal, right? And this op-amp is a difference amplifier, so it amplifies the difference between two signals. Let's say the differential input signal is VID. Differential input signal is VID, since it's a difference amplifier. Now, how the output voltage will be related to the input differential voltage? If the gain of the op-amp is, let's say, A, so gain will be equal to output voltage upon input differential voltage VID, right? So output voltage V0 will be equal to A into VID, A into VID. So to realize it, we need a dependent source, voltage dependent voltage source, that is the controlled source, right? And inside the box we will write plus minus, and outside the box, that is the output voltage. That output voltage we have calculated, that is A into VID. A into VID, VID is the input differential voltage, A is the gain of the op-amp. And this is actually the Thevenin equivalent voltage, and similarly the output resistance, it will be R0. So this is the equivalent circuit of the op-amp. So in this equivalent circuit, you can see that input voltage is VID and the output voltage is A into VID, input resistance is Ri, input resistance of op-amp, and the output resistance of op-amp is R0, right? This is just the equivalent circuit to understand the op-amp. Now coming to the operational amplifiers advantages. What are the advantages of operational amplifier? If we take some IC like 741 IC, so there we can understand it better. For 741 IC, right? The first advantage of 741 IC, here see the advantages of operational amplifier is, the first advantage is it's a difference amplifier, so the effect of noise is very less, and input impedance is very high, output impedance is very low, CMRR is high, slew rate, it should be high, right? Similarly, the bandwidth should be high for any op-amp. So there are various op-amp integrated circuits are available in the market, but one of the most popular op-amp IC is 741 IC. It is having 8 pins. It is having 8 pins. So as far as 741 IC is concerned, So the first advantage of this 741 IC is it is having short circuit protection circuitry. It is having short circuit protection circuitry. It is very important because if the current flows rapidly at the output, then the output transistors may get damaged, right? In order to protect the output transistors, there is a short circuit protection circuitry inside the 741 IC at the output. And the another advantage of this 741 IC is it is internally compensated. It is internally compensated IC. It is internally compensated IC. Now what is this compensation? That is called frequency compensation. This frequency compensation is very much required in multi-stage amplifiers, right? When we go for more than one stages like 2 stage, 3 stage, 4 stage, then due to comparable poles and zeros, the stability of the multi-stage amplifier, it suffers a lot, right? We know that for any circuit to be stable, the gain margin and phase margin should be positive. Gain margin and phase margin should be positive, right? So we need to compensate the multi-stage amplifier, and this op-amp is a multi-stage amplifier. So to compensate that op-amp, to stabilize that op-amp, we use some frequency compensation technique, and one of that technique is Miller compensation. One of that technique is Miller compensation. So in Miller compensation, a capacitor of a certain value is connected across, we can say it is connected between output and input of the high gain stage, right? So in case of 741 IC, already there is a capacitor of the value CC, that is called compensation capacitor of the value 30 picofarad. It is inside 741 IC, and the role of this compensation capacitor is to stabilize the IC, So suppose that if there is no internal compensation, then in that case we need to stabilize that IC, and for that we need to connect a capacitor externally. But this is not the case with the 741 IC. Already inside 741 IC, a capacitor of 30 picofarad is fabricated in the second stage to stabilize the op-amp. This is the another advantage of 741 IC. So these two advantages are there with 741 IC. Apart from this, 741 IC, it is having high gain, high open loop gain. It is around 107.7 dB. Open loop gain is very high. Input impedance is also very high. Input impedance is very high. It is in mega ohm range. In mega ohms range, and the output impedance is very low. It is in ohms range. And when we talk about the bandwidth, gain bandwidth product, that is also called unity gain frequency. For 741 IC, it is around 1 megahertz. It is around 1 megahertz. As far as slew rate is concerned, slew rate is a concern for 741 IC. Slew rate of 741 IC, it is less. It is around 0.63 volt per microsecond for 741 IC. So you can see that the slew rate is less. Like for ideal op-amp, the slew rate should be infinite. Obviously, we want that for any circuit, the slew rate should be high. But for 741 IC, it is 0.63 volt per microsecond. But for a particular application, if the slew rate required is high, then we can use other op-amp ICs like LM318 and other ICs also available in the market, which is having higher slew rate and higher gain bandwidth product in comparison with 741 IC. Now coming to the block diagram of 741 IC, like I have already discussed the block diagram of operational amplifier. If we talk about the 741 IC, that is the major topic of unit 1, right? So in 741 IC, the first stage is the differential amplifier. The first stage is a differential amplifier, and inside the first stage, that is the input stage, there is a level shifter circuit, and the first stage is having active load. That is the another factor, because when we design differential amplifier, it can have a passive load like resistor, it can have a active load like transistor. Like you people had studied in analog circuits, differential amplifier with resistive load, differential amplifier with active load, and in active load we had used current mirror, right? So here again inside the 741 IC, if you refer the internal circuitry of 741 IC, so the first stage is the differential amplifier, and the load which it is having, it is active load, and the advantage of active load is it provides higher gain. Now coming to the second stage of 741 IC, that is also called the gain stage, because the second stage, it consists of common emitter amplifier. And one more thing, 741 IC, it only uses BJTs, not MOSFETs. Fine. BJTs, along with BJTs there are resistors, and there is one capacitor of 30 picofarad value which is used to stabilize 741 IC, and that stability is achieved with the help of frequency compensation, and that frequency compensation technique which has been used inside the 741 IC, that is called Miller compensation. So in the second stage there is a Miller compensation, and that Miller capacitor connected, that is CC, and it is of the value 30 picofarad. So second stage, it provides the highest gain. And as far as the output stage is concerned, the output stage, it is basically the voltage follower stage, and it utilizes the class AB output stage. Whatever I am discussing here, it is only for 741 op-amp IC. Fine. Now coming to the input transistors of differential amplifier, second stage and output stage. The input transistors are in common collector configuration. If you see the internal circuitry of 741 IC, then you will see that the input transistor of the differential amplifier is the common collector. The input transistor means the transistor at which we are applying the input signal, right? That is again the common collector, and in output stage that is again the common collector. That is also called emitter follower, because the advantage of emitter follower circuit is it is having high input impedance. That's why in 741 IC the input transistors are emitter follower. If it is having high input impedance, then there will be no loading effect, their signal loss will be very less. That's why we have used this common collector configuration. This is just the basic description of the 741 IC block diagram. And as far as differential amplifier is concerned, this differential amplifier is it utilizes BJTs, and along with that those BJTs, it is having active load, right, to increase the gain. And after that, the second stage, it is basically the common collector, that is the input transistor, and after that followed by common emitter configuration, which provides the highest gain. Fine. And when we calculate the voltage gain of this 741 IC, so to calculate that voltage gain, what we will do, let's say the voltage gain of the input stage is AV1, the voltage gain of the second stage is AV2, and the voltage gain of the third stage, output stage, is AV3, and output voltage is V0, input voltage is, let's say this is Vi. So what will be V0 upon Vi? V0 upon Vi, it will be, since all the stages are connected in cascade mode, so the voltage gain, it will get multiplied, that is AV1 into AV2 into AV3, AV1 into AV2 into AV3, right? And this 741 IC is a direct coupled amplifier. It's a direct coupled amplifier. You can see that the output of the first stage, it is directly connected to the input of second stage. Output of the second stage is directly connected to the input of the output stage. There is no coupling capacitors involved to interface the stages. That's why it is called direct coupled. And there is another kind of amplifier that is called capacitively coupled. In capacitively coupled, we use additional coupling capacitors to couple the stages. But in IC, we avoid these coupling capacitors because the size of the coupling capacitors are large, and it is not possible to fabricate large values of capacitors inside the IC, right? So that's why this 741 IC is a direct coupled amplifier. So we can say that this 741 op-amp IC, the first point is obviously it's a op-amp, so it's a difference amplifier. The second important thing about 741 IC is it's a multi-stage amplifier. Obviously, if it is multi-stage, then it will provide high gain. Like the gain, the voltage gain of 741 IC for a particular value of a load, it is around 107 dB. That is more than 100 dB, right? And another important point is this 741 IC is direct coupled. Normally, IC amplifiers are direct coupled. We don't prefer coupling capacitors inside the IC because of the larger size, right? So this is about the voltage gain of this 741 IC. And after that, coming to the frequency response of 741 IC. So the frequency response we can draw for 741 IC. So to draw the frequency response, on x-axis there is a term frequency, and at y-axis normally we take gain, and that gain is voltage gain, and that gain is in dB. So when we draw the frequency response of 741 IC, or we can say that of any amplifier IC, the graph is like this one. At low frequency the gain is high, and as the frequency increases the gain starts decreasing, right? But in case if we had used coupling capacitors, then due to those coupling capacitors at low frequency the gain will be reduced. Normally when we go for discrete circuit amplifiers, when we design amplifiers on breadboard, there we use coupling capacitors, and there when we draw the frequency response, there you can see that at low frequency the gain is reduced, at high frequency the gain is reduced. There the gain is reducing at low frequency because coupling capacitors reduces the voltage gain at low frequency. But for any amplifier whether we are using coupling capacitors or not, at high frequency the gain will be reduced, because at high frequencies the gain is reduced due to parasitic capacitances, due to internal capacitances. And of course, when we are designing amplifier, it means that we are using transistor, and there are various internal capacitances present inside the transistors, whether it is BJT or MOSFET. So at high frequency the gain will decrease, because of the parasitics. But here at low frequency the gain is highest, the gain is not decreasing because we are not using any coupling capacitors. And this maximum gain that we have calculated, that is 107 dB. Although I have directly mentioned the value, you can calculate it just by calculating AV1, AV2, AV3 and multiply them. You will get around 107 dB for a particular load resistance, right? And the roll-off rate of this curve, it is minus 20 dB per decade, and that is because of the pole, and that pole is because that pole is the dominant pole, and that pole is coming because of the Miller compensation, because of that compensation capacitor CC that is connected across second stage, that is connected in between output and input of the second stage. Fine. And here there are two important frequency terms. One is minus 3 dB frequency. This frequency, let's say this frequency is FP. FP is the dominant pole frequency, that is the minus 3 dB frequency. And another frequency of interest is this one. Let's say this frequency is FT. So we can see that at FT the gain is 0 dB. So we can say that this FT is basically unity gain frequency. This FT is unity gain frequency. Unity gain frequency is the frequency at which gain is unity, gain is 1. If gain is 1, that is the ratio, and when you convert this ratio 1 into dB, 20 log 1 will be 0. So that 1 is equivalent to 0 dB. That 1 is equivalent to 0 dB. So the unity gain frequency is the frequency at which the gain is unity or 0 dB, and this unity gain frequency, it is also called gain bandwidth product. It is also called gain bandwidth product. And when you calculate these values like dominant pole frequency, FP, that is the minus 3 dB frequency, that is the cutoff frequency, and FT for 741 IC, this FP is around 4.1 Hertz. This is the numerical value for 741 IC. For different ICs, these values will differ. And for 741 IC, this FT unity gain frequency is around 1 megahertz. So you can see that the gain bandwidth product is limited to 1 megahertz, right? For many applications, the gain bandwidth product required, it may be high, it may be 100 megahertz, it may be 200 megahertz, 500 megahertz. There we cannot use this 741 IC. There we use those op-amp ICs for which the unity gain frequency is more, right? But once we understand the process of 741 IC, how we calculate, how we do the DC analysis to calculate the collector currents, DC collector current, how we do the AC analysis of 741 IC to calculate the input resistance, output resistance, and after that, once we understand that how we calculate FP and FT for 741 IC, once we understand for 741 IC, we can apply those concepts to other op-amp ICs, That's why this 741 IC is very basic. So basically in this class, I have discussed about what is operational amplifier, what are the advantages of operational amplifier, block diagram of operational amplifier, then after that equivalent circuit and schematic symbol of op-amp, and then I have discussed about 741 IC, and for 741 IC, the values I have discussed like overall voltage gain, input impedance, output impedance, then slew rate, and followed by this frequency response, right? Thank you.